Okay, no problem at all. So, Nikhil, I'm going to spotlight you now. We had a chat, I guess, about a month
That is
ago.
right.
Um, and I got far too excited about what you're working on. It was, I was like a schoolboy, meeting a footballer or something. It was crazy. Let me set the scene on Nikhil. So he works for TechMahindra, a very friendly company of MKAI, who's supported us in lots of ways in the past. But you are nowhere near Milton Keynes, as it happens, different continent. Nikhil is the head of the Maker Lab, the thin-q-bator division at TechMahindra. And his experience and passion, obviously around AI, but particularly around NLP, natural language processing. So at this lab, the primary objective is to understand intelligence at its primal level and then apply it to create intellectual property or solutions that directly benefit customers and their employees. For example, they've got robotics, both the physical type and the augmentation automation software. Machine learning with a focus on NLP that I mentioned, but also recurrent neural nets and deep belief networks. You're going to have to tell us more about that. And IoT as well. Raspberry Pi's beaglebones, Intel's Edison, microservices, AR, augmented reality. And Nikhil has a personal robotic assistant in his lab that guides visitors to meet himself. And wait for it, he's creating a holographic agent for himself too. It's definitely a night of exciting introductions. Nikhil, great to see you.
Well, thank you so much, Richard. I follow the light that Dr. Kosman threw upon. So from folded arms to folded hands, this is actually hello from India. And your permission, I hope it's not death by PPT. I'd love to share something with the community and possibly take it all from there, yeah?
Sure, you should have permissions, yeah. So we're going to run for, if we can go till 1750, I'm sure Jason will step in anyway, make sure we keep to time.
Yeah. No, so I think JT set up the context with how psychology can be brought into AI. I just want to do an up on the ante, maybe, and fingers crossed JT doesn't catch me after this. But the ideology is, how do you actually bring it beyond the neural networks? How do you essentially take it from a level of what AI today is? And this has been part of my research that I've been doing with from the last 5 years. But also, this journey really started off with IBM when I was a part of it, and it's been like that ever since. So quickly through the slides, I think I have about, say, 16, 17 odd minutes. I think Richard, you covered most of the mission and vision. I think I came back to India in about 2014. I was in US for a period of about 5 years. I think the sector in India was growing at that time. The government was quite conducive to doing a lot of innovation. And this is where the mission and the vision really started off. And we started off this R&D sector under the chief innovation wing in TechMahindra that I handle, called Makers Lab. And you've basically set the mission. You've said that the ideology is that AI, ML, in a lot of ways today, in industries is used as a misnomeric term. But can we get a little deeper into AI and ML? Can we understand it a little bit more better? Was the whole ideology on which the lab started off. Now, the philosophy, obviously, and my philosophy from 2004 was obviously rooted based on history. All of you know this. I know I've kept these slides over there. It all started off in 1939. You know the machine. You also know the people who actually solved it. I'm talking to none other than Alan Turing. But you also know that there was a test that actually that became very, very famous. And this is something that we try and solve. With almost every algorithm that we do, we try and make it more Turing compliant, and no prizes for guessing. The Turing test has become possibly the most common test across all. But if you look at it closely, and just for brevity's sake, the Turing test really says if there's an evaluator, he's hidden, by a partition between a computer and a human. If he cannot distinguish after asking questions to a computer and a human being, then the computer has supposedly passed this test. And that is called Turing test. But I think if you look at it closely, and I looked at it very, very closely in 2006 and 2007, and I found that it may be an imitation game. And the whole premise is actually set up on the fact that if you can mimic intelligence, you're deemed intelligent. And the ideology that if I can actually replace that computer with another human being, and I can talk in a language which is unknown to, let's say, the one that has just put in as a computer, I can still give him some kind of a guideline as to what the answer would be. this evaluator would still not be able to figure out whether he's actually talking, to the person who knows the language, let's say Chinese, or he doesn't know the language at all. And this led me into understanding the brain in a lot of sense. We've been doing a lot of research on neuroscience, particularly from a language perspective, which I'll come later, but also a large perspective of how AI really deals with shock and surprise. So what you see over here are certain experiments that we did about 2 or 3 years back, where AI does produce a largely negative results, or you can say as false negatives or whatever. The idea is that, and my favorite of these images is this cat with its head in the sandals or the shoes. And about 65% of my machines that I trained with vision actually called it a polar bear. The idea was you couldn't see the cat whiskers and the cat face, etc. And that is why the AI reacted in this fashion. And the other good example is this chair. It's an obfuscated chair. A lot of AI models that I trained in initially pick it up and they say it's a violin, rather than a cut chair, because these are obfuscated images. So AI is still hindered by shock and surprise. It works within a domain and context, as JT rightly mentioned. And the idea was, can we make it a little better? And this led to us discovering what could be the cortex. And I'm just briefly touching upon some of the experiments that were done, some of the experiments that are well known in the neuroscientific community, of course, in the psychological world as well. But it appears that the cortex that the human brain possesses has only got one algorithm. And these are some experiments that were done with mice, of course. Now, the ideology of this experiment was very simple. I think the left-hand side, what you see as a diagram is a nerve that is connected with a hand to a somatosensory cortex, so the part which basically looks at touch. If you pick up that nerve, and scientists really did it with the mice, they actually placed it to the retina. That region of the brain that was supposed to feel touch really started seeing in the real meaning of the word see in less than 3 months. And they did it with the auditory response, where the auditory section of the nerve was actually cut and placed to the retina, and that the same result really happened, indicating that the human brain has only got one algorithm. And that algorithm really looks at a large amount of data that it collects from senses, and it essentially hones itself based on that. Whereas when you look at AI, when you look at some of the things that we are doing on AI, there's a large connotation of what we look at from a statistical point of view, and we try and fit it to a curve, we try and fit it to a pattern. So this was one of those intents that actually started me looking into this field and doing a little bit of a research as well. Now, on your left-hand side, what you see is the reptilian brain, and it's got all the facets of reflex behavior, autonomous behavior, the emotions of obviously, and the spatial memory. And on your right-hand side, you have the human brain. Well, it's 75% similar, and which also goes to the facet of evolution that we have evolved from reptiles. But there's only one portion that makes us us, which is this neocortex, a small portion that is present as a wrinkled sheet of paper. And it covers about 75% by volume of the brain, but it's important to give you almost the entire sensory motor neuron model of the world. Our beliefs, our faith, our disbeliefs, etc., all lie at this small sector of that neocortex. And that is what makes us us. Now, what is our ideology? We're not creating a sentient being. We are not really going into that facet. What we are trying to look at it is, what is the seat of intelligence? What's the seat of connection? And can we bring out some of these elements into the next level of AI that we are trying to build in? Now, this experiment is pretty well known in the world of neuroscience and psychology. I think Dr. Crick at some point in time was dissecting a brain, and he incidentally dropped a dye in one of those regions. And when he actually looked at one of those regions, this is what he gets, right? It's a hierarchy of regions. Regions are remarkably similar across space and modalities. So all regions typically perform similar functions. And they all perform in 1 or 2 or 3 different ways. They recognize sensory sequences, they recognize motor neuron sequences, and they generate that motor sequence that we want for this world to do. So essentially stating and deducing that it is a single sector. There's only one function that the brain does, which is it predicts in the future. And if it doesn't predict in the future, it essentially passes on to the higher cortical sections, whatever region of the brain cannot decide. And it essentially goes on from over there. So ideally speaking, that is what the cortex really does. The neocortex learns a model from the fast changing sensory data. It does predictions, it does anomalies, it does interactions as well. The cortical theory, however, is basically based on the same phenomena. It is based on these hierarchy of identical regions. It says that there's a sheet of cells. It also says that these layers are probably divided into 4 or 5 of different columns. And each column, if you cut a cross-section of that column, it's got a lot of neurons, which are essentially responsible for what we are doing. This is how it appears. It appears in terms of layer 1 to 6. And the lowermost layers are really meant, they're all meant for sequence memory. We are all creating a sequence of information over a period of time. And our experiences over a large period of time is what we are today and what we really do and how we look at the world. Now, by definition, we have actually considered the lower 2 layers as feedback and the topmost layers as feed-forward mechanism. But this is what really happens, right? This is a neuroscientific view. Sensory data comes in, it essentially cuts into layer 4 and this is where the layer decides and tries to find out whether it can predict of what it is essentially seeing in the world. And for that, it has to go into the higher level of sequence memory. If it does predict well, it basically explains that mechanism and you have the answer. And I will come down to some of the thought experiments to do that. But if it cannot predict well, it essentially gives you as a kind of intent for you to learn. And this is where the whole model of the capacitance of what we build in into our synapse is really built across. Now, it's universal interface. If I give you as a feed-forward mechanism, if you learn 1, 2, 3, 4, 4, 5, 3, 2 as a sequence that comes on the right, and if that sequence is well known and you understand and you can predict the sequence, anytime I would give 1, 2, 3, the answer would be 4. Anytime I would get 4, 5, 3, the answer would be 2. If that prediction is valid, you have the right response. If that prediction is not valid, you get a certain bit of a different response from the brain itself. Now, I think the biological neuron and what we do with neural networks today, and if you've really looked at neural networks from a diagrammatic point of view, they are very, very densely connected systems. A lot of data to the input and a lot of data gets out of the output. But whereas what brain does and what we've seen within the neuroscience experiments is it's a sparse representation. Any input signal that comes into the brain is essentially taken care of by about, there's a sparsity of about 20% to 40% that is maintained. And this signal is not huddled at one corner of the brain. It essentially goes on and it affects a large portion of the brain on the other side as well. And this is possibly a difference from a dense representation factor that we do in neural networks to something that we are doing that only 2% of bits are possibly active at one point in time in terms of silicon. If we want to mimic this structure. Now, this is an example of a silicon-based neuron. This is an example of, how a neuron may really react if it's essentially being done with the same inputs or same outputs. But there are some practical examples to it, right? So some practical examples to it is that we have seen that the brain really shifts on memories. And there's an anecdote about a lady that had gotten the 9/11 kind of a facet. And she was basically, when she was interviewed after 18 years, her memories had completely shifted. What she remembered and what she had intook as a system of what she felt at that point was a complete 180-degree parallel shift to what she was speaking about. And this is also an example how brain really looks at these memories and really shifts those facets around. This is a thought experiment. And if I give you a word like, for example, APP, considering what you have been going around or doing in the past few days, few hours, few seconds, you'll be able to complete this. For people in computer science, you'd possibly call it application. For people in, for people in the food industry, they would call it Apple or something like that. But at any point in time, the regions of the brain are essentially predicting that facet. And they're essentially trying to tell you that this may be the answer. If the answer does not match, then the brain essentially passes on as a kind of an anomaly, and you essentially get to learn on that anomaly itself. Now, this is something that we've seen it as a WhatsApp, message that has been passed along across the world. All of you, and the WhatsApp message says, you can guess this, you're the smartest in the world. Almost all of us, barring few that I've seen, we are all the smartest in the world because all of us know these words. And what is being done is just the shifting of the word, but the brain has not seen those entire words as such. It only reads the first 2 or the 3 letters. It reads the last letter. it creates an image, it creates a prediction value based on those sequence layers, and it actually gets out the meaning of that word without actual spelling of the words being there. And my research and my team's research has primarily been on language, and language is the one that actually distinguishes us, us as a species. Language is the one that I'm speaking in. The ideology of language and neuroscience being connected, we have actually taken it back to the old Indian system, and we are essentially researching on Sanskrit. We are also researching on some of those Vedic principles to understand this. Why do we want to do that? Of course, there are lots of myths. I think one of the myths and one of the things that gets percolated across different WhatsApp groups, different channels, is something saying that NASA is using Sanskrit. Sanskrit's being spoken here and there. I think buying all those toy stories that we hear, the ideology of Sanskrit is such that it has got a rigorous grammar, and it helps us understand a large sector of languages that the Indian system has. Now, working in India, working with some of the efforts with the government, we do realize that India is a land of 1645 dialects and has got about 26 mother tongues. You try and force fit any model of neural machine translation or anything that you do with a dialect that is being spoken on would never work in India. And that's the reason why we have actually chosen the core of it, where all languages possibly reside. And there are lots of other myths, like, for example, the Southern Indian languages could not be dependent on Sanskrit. I think Sanskrit possibly guides almost an entire sector of languages in India, including the least variant and the least connected language, Tamil, which also has about 71% similarity with what Sanskrit really does. And the ideology is really built upon old Indian grammatical theories. And these Indian grammatical theories really look at the means of communication as a language, but also how does a human really express a thought which gets converted into speech, and how does the listener really decode that information when somebody's speaking to him or her. And these were the pivotal points which have been spoken, or which we find information in some of the Vedic texts. But we also are now trying to apply it into a modern, a scientific principle of an AI. Now, this is at its very best. If you look at it, when I try and speak and convey a word or convey something, our thoughts are actually a continuum. It happens in almost every second. You're having a thought in your brain. Whereas the language that we speak, whether it's English that I'm speaking or any other Hindi or other language that I speak, has a discrete lexicon. If you look at the speed and the wavelength of the two languages, they work at different bandwidths, and there's a huge trade-off. Now, there is always a trade-off between brevity and precision. When I want to speak to you and when I want to convey my message to you, I would like to be as brief as possible, but I'd like to be precise. But that's not possible because the mechanism and the bandwidth between the two worlds, which is the thoughts proclaimed into the lexicon, is essentially very, very different. And that has been an area of research which we feel that was cracked up by the old Indian grammatical theories. Now, what were these? Language, and one part of it are basically strokes. If you look at this, what I've given is I've actually given a little bit of strokes over here. I've drawn this with paint, etc. But if I was to really draw this well, this is nothing but a picture of a mouse that I want to give it. And this mouse really essentially represents in a broader way what I wanted to convey as a thought, but I could not convey it unless and until I use certain lexicons and words of the language. This phenomena, and possibly one or two last slides, but this phenomena goes back to the old Indian Sanskritist or linguist called Panini. Panini's genius was essentially to understand two things, or three things rather. How is the information encoded? Where is this information encoded? And what is that information that language should convey so that we can understand natural language processing, but we can also understand and convey that message as a thought to another human being. Now, NLP, a lot of people say has been solved. NLU, a lot of people say have been solved. My belief is that we are just starting. We know that we've done credible amount of work in neural networks, including the long short-term memory and the recurrence parts. But we still believe that there's much more that language can actually bring in, because we see shock and surprise almost every second day. The Panini's genius, and if these are some words written in Sanskrit, I'm very sorry if somebody doesn't understand, but I'll try and explain the meaning. If there's a sentence in English which says the man goes to the village, the Sanskrit word out of it, if I may speak, is Purusha Gramam Gachati, which really means is that the man is going to village, translated into Sanskrit. Panini's genius was actually to find out that the information is not encoded in the noun, the information is not encoded in the pronoun, the information is probably encoded in the word or in the verb, sorry. And if I change this sentence to just these two words and even cancel out the first word, this gramam gachati with 1/3 or 2/3 of the word that you have as a sentence still means the same thing. Whereas if you would connotate it in English, it would say village go, which possibly may not mean the same grammatical sense or make the same grammatical sense. In that similar fashion, if you only replace the words and even say only gachati or the last word, it essentially means the same thing. The language in itself, the information gets encoded because of the verb and certain other 4,000 rules that are obviously there, which we can't go through. But the idea behind this is that this language and this neuroscientific thought really proclaims well as to what we can look at from NLP. And that is my research, and that is all that I wanted to share with you. That this is what we've been researching on. This is where we combine the power of AI, neuroscience, and linguistics, and we're trying to solve problems for the subcontinent. So thank you.
Thank you, Nikhil. I think tremendous talk, isn't it, Richard? Would you agree?
Wonderful. I'm glad I recorded that. It's going to be a couple more watches, then I'll be able to get back to you, Nikhil, with something sensible, I think, in response.
Yeah, absolutely. And we have already had a couple of questions that have come in. But Nikhil, thank you. Thank you for this wonderful talk and how, neuroscience is the evolving era that we are looking at, and how we can replicate the brain, how neural networks are missing out on hierarchy, temporality, and memory as well. And, how you are using the Vedic system and Sanskrit in order to put into AI and the algorithms for the success of it. I think that's something, to bring about the brevity that language has and the context that language has, and how strong language makes us as human beings and different from AI. I think that is what is interesting from your talk. I think brain science is what Naima called it, and I think that's what it is. Thank you. Thank you so much for your talk, Nikhil.
You're most welcome. Thank you so much. It's a pleasure, Jessel. Thank you.